Okay, welcome to the start of our Coriolis lectures. And as I often do, I'll start by just commenting on where we've been so you can appreciate where we're going. So, in the relative motion analysis that we've done to this point, as we've gone from one link to the next link, what we had is that the links were connected. So whatever point O on this link did, point O on that link did. Now that's ground, it's not moving, that's kind of boring. But if you look at it this way, A exists on link 2 and link 3. And in fact, it's the same point. So whatever A does on 2, A does on 3. Okay? And when we had that, then we simply moved from a point A to B by omega cross R and omega cross R minus omega squared R. And just walk through. And we might walk through from the other side as well to create more equations, but that's all it is. Okay? That's all it is. Now, suppose we have a bit of a different scenario. Suppose that this point A, there's a point A on link 2 and on link 3, but they're not connected, so that the relationship changes. What do I have in mind? Because that's going to sound, no doubt, a little strange to you. You're probably listening going, what? Well, let's just consider that. So I'm going to consider a very specific scenario, which is written here. Consider the connections between links 2 and 3. So up above here I had link 2 and 3, but we're going to change it. So what happens now is link 2 connects to link 3 at the same spot. So 2 touches 3 at the same spot on 3 all the time. But link 3 connects to 2 at a whole bunch of different spots. Okay, this is kind of weird. 2 connects to 3 always at the same spot. 3 connects to 2 at many spots. So how do you do that? Well, actually a merry-go-round will do it. So let's go through that. So here we have a picture. This is a merry-go-round. And I've had students through the years, they go away, they say get married, have kids, and they'll go do what I'm going to suggest that you do, and they're like, wow, this really works. So here's what you do. At some point when life goes on for you and you have your own little buckaroo, and you go down to, say, Disney. You want to do this on a really big merry-go-round that's got a little speed to it. Okay. So you get your significant other, say, to stand outside and do the waving. So, because in my experience when I was young, it was often with my wife and I when we took our kids, one of us was on the ride with the kid and the other one was outside, constantly waving at the kid, giving encouragement. So maybe you'll do something different, but suppose you'll want to be on this ride. So picture merry-go-round. So you put your little buckaroo there on the horse, okay? And you can be taking pictures, and the camera will give you a good excuse because you're really not caring about taking pictures of the kid. What you want to do is feel in your feet what's happening. So the camera will give you an excuse for kind of walking around the kid and kind of feeling what's going on. So here's what you do. You kind of walk around the kid on the horse, and then then try to walk in a straight line to the center of the merry-go-round. And then you can kind of walk around and walk straight back out from it. What you'll feel is, especially when you're on these paths, is there's going to be some strange, bizarre force if you just focus. And it's not very big. It's subtle. There's a force that's saying, no, you don't want to walk on this line. It's going to try to push you off. It's not so strong you can't do it, but it's strong enough that you will have to put a little thought into seeing the line and staying on it. Okay? That force wanting to take you off these lines? Coriolis. Okay? Coriolis wasn't noticed. I'd have to go check Google to find out when it was discovered, but it's been within the last 150 years or so. And it was discovered, as I recall, as a mathematical remnant, and then they looked into it and go, wow, this is real. So if you look, but let's look what's happening here. The merry-go-round will be link 2. It always connects to you at your feet. It's connecting to you at the same place every time. However, you are connected to the merry-go-round all over the place, and you can walk all around. And so you connect in multiple places to the merry-go-round, but the merry-go-round always connects to you in one spot. Got to emphasize that. It's in one place. All right. Well, given that, this is relative motion analysis, but when you don't have this rigid connection, you can't do it via these equations to go, say, from A to B. Here's what you have to do. Let's call where your feet are on the merry-go-round a point A. So here's the point I want to get. Point A on you with the camera, with your little buckaroo, is at the base of your feet. Okay, so there's a point A on you, and there's a point A on the merry-go-round. But those points are not fixed together. These are all the potential A's on the merry-go-round. These are and there's only one A on you. So here's what you have to do, is that when you're analyzing stuff, is you'll take the merry-go-round. You know how fast the merry-go-round is going. The real question is what are you feeling, velocity and acceleration-wise? All right? So what you have to do is figure out at a given A what the merry-go-round is doing, and then you have to transition. So you'll have A on link 2, and then you have to do a jump to A on link 3. And then you can continue on as you did before. All right? So here's the difference. In here, you didn't have to make a jump from A on link 2 to A on link 3. It was just done. It was automatic. It's the same point in both places. A on link 2 and A on link 3 are the same point. In here, they're different. So you'll figure out A on a given link 2, and then you'll have to do a jump to A on link 3. Okay? And from there, if things are rigidly connected, you just go as you did before. But you have to make the effort specifically to jump from link 2 to link 3 at the quote-unquote same point. And that is where Coriolis comes in. All right? And the key here for Coriolis is link 2 touches link 3 in only one spot. Link 3 touches link 2 all over the place. Okay? And so when we set this equation up, we need to know what is link 2, the thing touched everywhere. What is link 3, the thing touched in only one spot. Okay, you got to keep that straight. Given that, here's how you do the jump. From the merry-go-round to your feet. It's simply velocity of A in link 2, which we can get conventionally, no problem. And then we have V A3, A2 relative. What does this mean? That REL is really important. What this says is, if you were laying down on link 2 and watching the person move, okay, so it's like this is ground for you, the merry-go-round. What do you see the person do? Not does somebody outside the merry-go-round see. If you could lay down and watch this person move, what does the person on the merry-go-round see? That's what that is. Relative velocity, relative. Okay, so it's kind of a double. It's A3 relative to A2, but from the relative perspective, not the ground perspective. Everything we did up here was always from a ground perspective. We didn't really talk about that, but that's what was going on. This is from the relative perspective. All right, for acceleration, how do we make the jump? A2, we can get the acceleration anywhere on the merry-go-round by conventional means. Alpha cross r minus omega squared r. Bam, zip, done. All right. But we need to make the jump then from 2 to 3. And that's done by the following. And this is the Coriolis acceleration term. It's 2 times the cross product of omega A2, so the merry-go-round. So this is sometimes you'll have this person, quote unquote, being a thing that rotates. And so then you get into question, which omega goes in here? This is the omega of the device getting touched everywhere. If you use a different omega, you're going to be all wrong. So it's the omega of the device getting touched everywhere cross this VA3A2 rel. Okay, if somebody's lying down in here, what do they see this person doing? All right, and then we have another relative term. And so this would be, again, if somebody lies down here, what would they see this person doing accelerating relative to the merry-go-round? Not from somebody outside relative to ground, what they think is happening. What do you see happening on the merry-go-round? Those are the keys to doing these problems. These equations are very simple to use. You simply need to do two things. One, if you don't have a clear connection, as you do here, you're going to have to make a jump from A on link 2 to A on link 3. If it fits this model, where 2 connects to 3 all over the place and 3 only connects to 2 in one spot, you're going to use Coriolis. If you don't have this scenario, you have a much more complex dynamic problem. You need another course in dynamics, and you ain't going to get that here. So you don't have to worry about it. But for the Coriolis situation, all it means is once you have the situation, note which part is which, and just plug and chug. And they're really very simple problems. These problems have a horrible reputation. And I remember taking this course when I was young, and this stuff really stunk. And one day, finally a light bulb went on, and I realized it's all about, because your book doesn't talk about it this way, one link touches one link touches the other all over, the other link touches the one in only one spot. As long as you know which one is which, you substitute those into there, and it's just plug and chug, and it's an easy problem. That's the difference between hard and easy. And starting next time, we start doing problems. Till then.